So we're looking at a system with two Hilberts, with two states in a Hilbert space. And Hamiltonian on that system we took to be what? Had some constant V0 here. E1.
We did E0 and E0
Huh?
before. I think we did E0 and E0 before.
We made them same?
Yeah, same. Special.
And we took two states, which I think we called 1 and 0, right? 1 and 2. So a Hilbert space of states was spanned by vectors psi, which will the form A1 plus B 0, 1, where A and B are complex numbers with the property that A squared plus B squared is 1. And then we constructed a set of three operators, so three observables. What it means is that these three operators, which we call as X, or Hermitian, and if I remember, they were given by H bar over 2, 0, 1, 1, 0, S bar was H bar 2, 0, minus I, 0, and S equals H bar 2, minus 0, 0, minus 0. And it is actually convenient, if you look at these three, that given a basis set, in other words, two vectors which are mutually perpendicular, by the way, the multiplication between vectors is defined as a matrix multiplication. So this is 1. 2, 1 is simply 0, 1, 1, 0. So this is 0. So this is how the multiplication is defined. So bra vectors you get from these by transposition and complex conjugation. You can see that only one of these three operators is diagonal in this particular basis. So for example, SC on 1 is simply H bar over 2, 1, and SC on 2 is minus H bar 2. And it is convenient and commonly done to actually hold these up or down vectors. This actually corresponds to a couple of important physical systems. One of them is a spin, 1/2. It's a physical system, which is a spin, 1/2 particle. So any spin 1/2 particle can be described by those. Something like electrons is described by state by the Hilbert space like this. Something like proton, muon, neutrino probably too, something similar to that. atomic nuclei which have spin 1.5 can be described like this. Now, something which is more complex will have additional properties, but will definitely have something like that. And so when I describe actually for you in more detail the electron in a hydrogen atom, you'll see how that more complex parts come to account. For the moment, we ignore anything more than just the basic property, which is a spin 1.5. And another important system which is described by this formalism is called the qubit, which is important in quantum computing and information. But just be mindful that qubit is nothing more just this thing under a different name. So qubit and spin 1.5 are basically they're identical systems. In principle, why this is useful for quantum information is because having only two states, this corresponds to open and closed, right, in logic. So that's how it works. If you look at actually the remaining two operators, they are not diagonal in this basis. For example, Sx on 1, which is easy to compute, is h bar over 2, 0, 1, 1, 0, 1, 0. And if you compute that, it gives you h bar over 2, 0, 0, 1, 0. So this gives you h bar over 2, 2. So Sx maps the spin up into spin down. And Sx, if you check on 2, will give you h bar over 2 spin up. These operators Sx, Sy, and Sz are commonly written in terms of so-called Pauli matrices, sigma I, where these here are Pauli matrices. And I'm interchangeably using notation where I can stand for 1, 2, or 3, or I can stand for x, y, and z. Doesn't matter. So 1 is x, 2 is y, 3 is z. It's just notation. How you can, and just for the record, sigma I, sigma j multiply this matrix is equal to delta ij plus I epsilon ij k sigma k, where you know the meaning of symbols. Okay. So one way to see the second relationship here, if we remove the h bar over 2, so for example sigma x on 1 is h bar over 2, and sigma x on 1, which is h bar over 2, which actually means that sigma x on 1 is 2. And one way to see this formula here is to apply sigma x twice. Right? Because of this relationship here. But on this side, this is actually 1 times 1, which is 1. So you get that sigma x on 2 is 1, or Sx on 2 is h bar. So it follows. You can do it also by direct computation, multiplying matrices. This is just another way of doing it. So, there are some interesting questions that we can ask. If I prepare a state, so prep a state that is pure, say up state. What is the chance that at some later time, so what is the chance, question, that at some later time, this state has spin in, let's say, plus x direction. So this is a question that we would like to answer. I mean, you can prepare the state any way you want, and you want to ask what is the question that at some later time the state is pointing not in a z direction, but actually it doesn't matter where it's pointing. What you want to do is you want to measure what is the chance that at a later time the spin is actually along the x direction or the y direction, either positive or negative. The question is how we do that. So we'll break down solving this problem into two parts. First, we will ask the question, if you have a state prepared to be spin up like this, what is the chance that at t equals 0, that state is composed of a particle or a state which actually has polarization in the direction of the x-axis or the y-axis. So in order to do that, we have to first find out what are the states which corresponds to projection of the spin in the x or y direction. I didn't mention it today, but as x as y conic pair is I as z and the cyclic ones. So this is actually this operator that we constructed is analog of angular momentum.
It was IH bar, right? IH bar?
Yeah, it is I.
Okay.
Yeah. And there was a formula that just reminds me that I wrote. Earlier, if you remember, I'm missing an H bar. Dimensionally, it doesn't make sense without H bar. Now, it is common in quantum mechanics to use units where H bar is 1. So if you use those units, then my formula is correct. So if H bar is 1, how much is H itself? Yes. Yes. Okay. So how do we answer this question? What is the chance? So initially, if we prepare the state initially to be like this, what is the chance that at some later time this spin has, that the state has spin in the positive x direction? And anyone dares to guess?
50-50.
Yeah. Wow. Sort of. Yeah. But first we need to find out, because in this particular basis that we chosen, SZ is the one diagonal, so it's measurable. These two are not diagonal, so they cannot be measured at the same time. So we actually need to first find the states which diagonalize this and this operator. So that amounts to basically kind of like a rotation in a Hilbert space, in a space of states, or rotation of the coordinate axis. You start with xy axis, let's say, in a plane, and then you want to rotate these axes to a different direction. And so that's what kind of corresponds to this process. So basically we need to solve the eigenvalue problem with this operator. And this equation has non-trivial solution if the determinant of the system is 0, which means that lambda squared is 1, or lambda is plus or minus 1. So, this is my eigenvalue equation, and now I need to find eigenvectors. So if I do that, B is plus or minus A, and A is plus or minus B. So you can see that two equations are compatible. So I have two choices. For lambda is equal to plus 1, we have the choice that B is A, and for lambda is equal to minus 1, B is equal to minus A, right? So for this case, the state will be something like A, and for this state, the state will be A minus A. Don't forget that the states in a Hilbert space satisfy this property. So regardless, we have 1 plus minus 1 squared is 1. And this is not 1. This is A. This is A. So we get that A squared is 1 half. Taking constants to be positive, A comes out to be 1 over 2, 1 over square root of 2. So then, easy. So basically, eigenstates of Sx are 1 over square root of 2, up, plus, down, up, minus, down, or in a matrix notation if you want. This is 1 over square root of 2, 1, 1, and this one is 1 over square root of 2, 1 minus. Now, I'll give you 3 minutes and you find the eigenstates of Sy.